Alright, let's go. Number 10. The Bostrom Argument. Nick Bostrom was not trying to prove that reality is fake. He was working on something far drier, anthropic reasoning, the branch of probability theory that deals with observation selection effects. How do you reason correctly when your own existence filters the evidence available to you? He had spent years on the doomsday argument and self-sampling assumptions. The simulation paper started as a footnote application of that same machinery. Here is what everyone assumes before he opens his mouth. You are a biological organism. Your body is made of carbon and oxygen forged inside dying stars. Your consciousness runs on roughly 86 billion neurons. And those neurons sit inside one universe, the original one, the only one, the base layer. Every experiment ever performed was performed here. That is the default position, and almost nobody defends it out loud, because almost nobody thinks it needs defending. Bostrom ran the population math instead. If any technological civilization ever builds ancestor simulations, it does not build one. It builds billions. One original history. Billions of copies of that history, each populated by minds that feel exactly like yours. Nick Bostrom. Are you living in a computer simulation? Published in the Philosophical Quarterly, Volume 53, number 211, in 2003. He never claimed we are simulated. What he constructed was a trilemma. At least one of three statements must be true. Either civilizations reliably go extinct before reaching that capability, or civilizations that reach it have essentially zero interest in using it, or we are almost certainly inside one already. 23 years of attacks have not broken it. Maybe consciousness is not substrate independent and only wet neurons can feel, but that is an assumption nobody has demonstrated. And if it were true, it would be the most important discovery in neuroscience. Maybe simulations at that scale are computationally impossible. Except Bostrom's estimate of 10 to the 33rd through 10 to the 36th operations for all of human history sits far below the ceiling Seth Lloyd calculated in Nature in 2000. Roughly 10 to the 50th operations per second on a single kilogram of matter. Maybe advanced civilizations simply lose interest, which requires unanimous, permanent disinterest across every civilization that ever arises, with no defectors ever. David Chalmers took a different route in his 2022 book, Reality Plus, arguing that a simulated world would be a real world rather than an illusion, which dissolves the horror and leaves the arithmetic untouched. Each escape route stays open. None of them closes. The part that lands is what this does to your memory. The weight of someone you loved. A specific afternoon in a specific year. The night you were nearly killed and were not. Under the trilemma, those experiences are either original or reproduction, and no measurement you can perform from inside your own skull tells the two apart. If a piece of arithmetic tells you that you are probably not the original, what exactly have you lost, and would you feel it go? Zeus asked the same question 34 years earlier, and he asked it as an engineer. Number 9. The calculating space. Konrad Zuse built the world's first programmable digital computer in a Berlin apartment in 1941, wiring together roughly 2,600 electromechanical relays around wartime shortages. The machine was destroyed in an air raid 2 years later. After the war, he was not chasing metaphysics. He was thinking about a constraint every engineer knows in his hands. Computation consumes space, time, and energy as physical resources, and no clever programming makes that bill disappear. That mundane observation is what took him somewhere strange. Physics since Newton has treated space and time as a continuum. Between any 2 points there are infinitely many points. Fields carry real number values with infinite precision, which means specifying the state of a single cubic centimeter requires an infinite quantity of information. Every differential equation in the standard toolkit assumes smoothness all the way down, forever, with no smallest unit and no update step. Quantum mechanics quantizes energy and angular momentum. It leaves the stage itself continuous. Zeus asked whether the universe computes, not as a metaphor, as mechanism. He published Rechnender Raum, Calculating Space, in 1969, proposing that the cosmos is a cellular automaton and the smooth equations are an approximation of something discrete underneath. Edward Fredkin at MIT spent 3 decades developing the idea. His 1990 paper in Physica D set out digital mechanics as reversible universal cellular automata. Stephen Wolfram's A New Kind of Science, 2002, argued that a handful of trivially simple rules generate the complexity we have been mistaking for continuous law. The objections are heavy, and they have not been answered. A fixed grid picks out preferred directions and a preferred rest frame, which breaks Lorentz invariance, and Lorentz invariance has survived every test ever aimed at it, to precisions better than 1 part in 10 to the 17th. Bell's theorem rules out local hidden variables, and simple cellular automata are exactly the kind of local machinery Bell excluded. The loophole-free experiment run by Ronald Hansen's group at Delft in 2015. And the awarding of the 2022 Nobel Prize to Alain Aspect, John Clauser, and Anton Zeilinger for that line of work closed the last escape hatch. Gerard Hooft's 2016 Cellular Automaton Interpretation of Quantum Mechanics tries to survive by denying that experimenters can freely choose their measurement settings, superdeterminism, a position most physicists consider unfalsifiable rather than wrong. Wolfram's own physics project, relaunched in 2020 around evolving hypergraphs instead of fixed grids, was built specifically to dodge the preferred frame problem and is yet to produce a single novel testable prediction. 57 years after Zeus, no discrete model reproduces the standard model. Everything you have ever touched has an edge: your fingernail, a coastline, the boundary of a cell. Physics has always insisted the underlying arena has no edges at all, no smallest tile, no pixel. Zeus's question is whether that insistence was ever tested or merely inherited. If the universe does update in discrete steps, what happens in the interval between two of them? And where are you during it? Wheeler took the discreteness 1 layer deeper, down to what the tiles are made of. Number 8. The It from Bit. John Archibald Wheeler had spent his career on the most material objects in physics. He worked on the Manhattan Project. He supervised Richard Feynman, Hugh Everett, Kip Thorne, and Jacob Bekenstein. 4 students who between them produced path integrals, many worlds, the LIGO program, and black hole thermodynamics. He spent decades on general relativity, on gravitational collapse, on the geometry of space-time. Matter and curvature, the heaviest subjects available. In his 80s, revising lecture notes on quantum measurement, he began circling a question about what the geometry was made of. The materialist picture is clean, and it has never lost an argument. Matter and energy are fundamental. Information is a description we impose on top, a bookkeeping convenience, a human category laid over particles that would go on colliding whether or not anyone was counting. The particle is real. The bit about the particle is commentary. Wheeler inverted the stack. He argued that every physical thing derives its existence from binary yes or no answers to measurement questions. The paper is Information, Physics, Quantum, The Search for Links, delivered at the 3rd International Symposium on Foundations of Quantum Mechanics in Tokyo in 1989. His phrase was it from bit. He was not speculating idly. The strongest supporting result predates him. Rolf Landauer at IBM in 1961 proved that erasing a single bit must dissipate at least kT times the natural log of 2 in heat, a hard physical cost for a purely informational act. Landauer's limit was measured directly by Antoine Brute and Eric Lutz's team using a single microscopic bead in an optical trap, published in Nature in 2012. Information is physical. That much is settled, and every data center on Earth pays the bill in cooling costs. What nobody has managed is the reverse derivation, getting space-time, mass, and charge out of pure information without quietly smuggling physics back in through the definitions. Wheeler's own participatory universe was accused of circularity from the start. Observers make reality, and reality makes observers, and the loop has no entry point. Efforts to rebuild the world from quantum information, including Anton Zeilinger and Aslav Bruckner's foundational principle program, produce elegant reconstructions of quantum theory and not 1 gram of gravity. Eric Verlinde's 2011 paper deriving gravity as an entropic force generated enormous excitement, and then a decade of technical objections it has not survived. 65 years after Landauer, "It from bit" remains a slogan with a rigorous proof attached to one small corner of it. Your body runs on this exchange constantly. Every memory you consolidate overnight and every one you discard has a thermodynamic price, paid in heat, measurable in joules. Forgetting warms the room you sleep in. If information carries a physical bill, who or what is paying it for the universe as a whole? Wheeler's bits have to be set to something, and the settings turn out to be suspiciously precise. Number 7. The dial problem. Fred Hoyle was not looking for evidence of design. He was working on stellar nucleosynthesis in the early 1950s, trying to explain a stubborn accounting problem. Carbon exists in enormous quantities, but the reaction that produces it inside stars ran far too slowly on paper to account for what we observe. He needed the rate to be higher. He worked backwards from the fact that he was made of carbon. The constants of nature are supposed to be brute facts. The strength of the strong nuclear force, the mass ratio between proton and electron, the cosmological constant, no theory predicts them. You measure them, you write them down, and you move on. There is no expectation that they should be balanced against each other, because nothing balances them. Then you check the tolerances. Hoyle predicted that carbon-12 must have an excited state near 7.65 million electron volts, or stars could not make carbon fast enough. Ward Whaling's group at Caltech found it that same year, 1953, within a fraction of a percent. The cosmological constant is worse. Quantum field theory's vacuum energy estimate exceeds the observed value by roughly 120 orders of magnitude, the largest discrepancy between prediction and measurement in the history of science. Steven Weinberg's 1987 paper in Physical Review Letters showed that if it were even modestly larger, galaxies would never have condensed. Martin Rees cataloged the problem in just 6 numbers in 1999. The strong nuclear force converts about 0.7% of hydrogen's mass into energy in stellar fusion. Shift that figure to 0.6 and only hydrogen exists. Shift it to 0.8, and hydrogen fuses away in the first minutes after the Big Bang. The neutron outweighs the proton by about 0.1%, which is the only reason free neutrons decay and free protons do not. Nobody has a mechanism for any of it. String theory's landscape offers perhaps 10 to the 500th vacuum states, converting fine-tuning into a selection effect while predicting nothing testable. A move attacked as unscientific by Lee Smolin and Peter Woit, among others. Eternal inflation generates the required ensemble and cannot be observed from inside a single bubble. Symmetry principles, which fixed so much else in 20th century physics, keep failing to fix these values. The anthropic answer is logically airtight and explanatorily empty. And the tuning gets tighter every time somebody measures more carefully. Every atom above lithium in your bloodstream passed through Hoyle's resonance. Shift that 7.65 by 1%, and there is no carbon, no oxygen, no chemistry, no reader. The parameter sits at a value that has never been derived from anything. If the settings had to be that exact, does anything follow from the word settings? Or is that just what dials look like from the inside? Wolfram found a different kind of limit, and this one applies even to whoever set the dials. Number 6. The irreducible computation. Stephen Wolfram was doing something unglamorous in the early 1980s, cataloging one-dimensional cellular automata by brute force. 256 elementary rules, each one a trivial instruction about black and white cells, each one run on a computer and printed out. It was taxonomy, not theory. He expected simple rules to make simple pictures and to finish the survey quickly. Prediction in physics works by shortcut. You do not simulate every second of an orbit to know where Mars will be in 50 years. You solve an equation and jump straight to the answer. That is the entire promise of mathematical physics. Understanding a system means finding a compression of it, a formula that outruns the thing it describes. Rule 30 broke the promise. Simple rule, random-looking output, no compression. To learn the state at step 1,000,000, you have to run 1,000,000 steps. Wolfram called this computational irreducibility and made it the spine of a new kind of science in 2002. Rule 30's output was reliable enough as noise that it shipped as the random number generator inside Mathematica, and in 2019, Wolfram posted a public prize for anyone who could prove its center column never becomes periodic. Nobody has claimed it. The formal backbone came from Matthew Cook, who proved that Rule 110, an elementary automaton statable in a single line, is capable of universal computation. The proof appeared in Complex Systems in 2004. Universality implies undecidability, and undecidability is not a statement about effort. Toby Cubitt, David Presgarka, and Michael Wolff carried the result into physics proper with undecidability of the spectral gap in nature in 2015, constructing a quantum many-body system whose energy gap is provably not determinable from its own description. The escape attempts run out fast. Maybe irreducible systems are rare curiosities. Except Wolfram's survey and 4 decades of follow-up point the other way, suggesting irreducibility is the common case and neatly solvable physics is the freak exception we happen to find first. Maybe quantum computers break through. They change the exponent on certain problems and leave the principle intact. Maybe better mathematics is coming. The undecidability results say specifically that it is not, for these classes of question, in the same way G-Del's theorem is not a request for more effort. Maybe irreducibility is a statement about our tools rather than the world, but Cubitt's construction concerns the system itself, and would still hold for an observer with unlimited computing power and infinite patience. This is the strangest item on the list, because it constrains the hypothetical simulator too. A universe like ours could not be run fast-forward even by whatever is running it. To know what you do next, it has to let you do it. If your future cannot be computed faster than you live it, in what sense is it already there? Irreducibility says the steps are mandatory, which raises the question of how small a step can be. Number 5. The smallest distance. Abhay Ashtekar was trying to fix the mathematics. In 1986, he reformulated general relativity into a set of new variables specifically to make it easier to quantize, a technical repair job on equations that had resisted quantization for 60 years. Carlo Rovelli and Lee Smolin picked up the reformulation in 1990 and started looking for solutions. The intent was housekeeping, not revolution. Einstein's spacetime is a smooth manifold. You can subdivide any region indefinitely, forever, and never arrive at a smallest piece. Every equation in general relativity assumes that continuity and 111 years of successful predictions, Mercury's perihelion, gravitational lensing, the 2015 LIGO detection, have given nobody any reason to doubt it. The solutions came back quantized. Area and volume operators with discrete spectra, not smooth. Grainy, the unit is the Planck length, 1,616 times 10 to the minus 35th meters, roughly 10 to the 20th times smaller than a proton. The matching interval is the Planck time, 5,039 times 10 to the minus 44th seconds. Loop quantum gravity spin network states, developed by Rovelli and Smolin out of Ashtekar's variables through the 1990s, hand area a smallest possible non-zero value. The area operator has a discrete spectrum, and the gap between allowed values does not shrink to zero. Wheeler had anticipated something like this in 1955 when he coined the term quantum foam. String theory reaches a comparable floor by an entirely unrelated route. Two rival programs that agree on almost nothing agree that space stops being divisible somewhere near this scale. Testing it has been brutal. If spacetime were a simple grid, high-energy photons should crawl fractionally slower than low-energy ones, and a burst traveling billions of light-years would smear that fraction into a measurable arrival delay. The Fermi Gamma-Ray Space Telescope observed gamma-ray burst 090510, 7 billion light-years out, and published the result in Nature in 2009, A 31 giga electron volt photon arrived within 9/10 of a second of its low-energy companions after a 7 billion year journey, which rules out that dispersion even above the Planck scale. The MAGIC telescope's earlier hint from Markarian 501 in 2005 never firmed up under scrutiny. Direct probes fare no better. The Large Hadron Collider operates roughly 15 orders of magnitude below the energy required. So the grain, if it exists, is either far smoother than any naive lattice or sitting behind an energy wall no instrument built this century will climb. Discreteness survives as mathematics and refuses to show up as data. Zoom into your own hand far enough, and the standard picture says you never stop zooming. Loop quantum gravity says you hit a floor, a scale below which closer together stops meaning anything. Resolution, in the literal sense. If there is a smallest possible distance, what determines it, and why that number? At the other end of the energy scale, cosmic rays run into a ceiling nobody ordered. Number 4. The energy ceiling. Kenneth Greisen at Cornell and Georgy Zatsepin with Vadim Kuzmin in Moscow were doing something routine in 1966, working out how cosmic rays interact with the cosmic microwave background on their way across intergalactic space. The CMB had only been confirmed a year earlier. This was straightforward bookkeeping about photon collisions along a long journey. The kind of calculation you do to clean up a model, not to overturn one. The prediction that fell out is sharp. Above roughly 5 × 10 to the 19th electron volts, a proton crossing intergalactic space collides with CMB photons energetically enough to produce pions, bleeding energy on every collision. Anything above that threshold that has traveled more than about 160 million light years should have been ground down below it. There should be a hard cutoff in the spectrum. Then Utah caught something impossible. On the 15th of October 1991, the Fly's Eye detector recorded a particle at 3.2 × 10 to the 20th electron volts, the oh my god particle. A single subatomic particle carrying the kinetic energy of a fast-thrown baseball, roughly 40 million times the energy of anything the Large Hadron Collider produces. The telescope array's Amaterasu event, published in Science in 2023, came in at 2.4 × 10 to the 20th. Both sit far above the Greisen, Zatsepin, Kuzmin threshold, and neither points back at a plausible nearby source. The suppression itself was confirmed by Hires and by the Pierre Auger Observatory in 2008, so the cutoff is real. The exceptions are the problem. Japan's Agasa array had reported around 11 events above threshold through the 1990s, and the disagreement between Agasa and Hires took a decade of detector cross-calibration to settle. Maybe the sources are closer than the statistics suggest, but the arrival directions keep pointing at unremarkable sky. Maybe the particles are heavy nuclei rather than protons, which shifts the threshold and does nothing about the acceleration problem. No known astrophysical object can plausibly push a nucleus to that energy. Maybe Lorentz invariance fails at extreme energies, a cure considerably worse than the disease. And in 2012, Silas Bean, Zore Davuti, and Martin Savage published Constraints on the Universe as a Numerical Simulation, pointing out that if reality runs on a lattice, the lattice spacing would impose exactly this kind of momentum ceiling, and would leave cosmic ray arrival directions faintly aligned with the grid axis. Nobody has found that alignment. Nobody has ruled it out. Roughly 1 cosmic ray passes through your body every second of your life, and a handful over a lifetime carry enough energy to break a strand of DINA outright. The particles at the top of this spectrum are the same phenomenon, scaled to something no accelerator will ever match. If the ceiling is real and something keeps arriving above it, is the rule broken, or is it not a rule? The cosmic microwave background hides a stranger claim, and it has been badly mangled in the retelling. Number 3. The Adinkra Codes. Sylvester James Gates Jr. was doing algebra. In the late 2000s at the University of Maryland, he was working on supersymmetry, specifically on a diagrammatic bookkeeping system for tracking how equations transform bosons into fermions and back. The diagrams were called Adinkras, borrowed from West African symbols. They were a filing method. Gates was trying to organize equations, nothing more. Supersymmetry equations are supposed to contain what you put into them: particle content, transformation rules, symmetry constraints. They are a description of physics. Whatever mathematical structure appears in them should be traceable to a physical assumption somebody wrote down. Gates kept finding something he had not written down. Adinkras are graphs, colored lines and filled or open dots, encoding how each field in a supersymmetric theory maps onto every other under the symmetry transformations. When Gates and his collaborators translated those graphs into binary strings, the strings were not arbitrary. Embedded in the Adinkras were doubly even self-dual linear binary error correcting block codes, the same mathematical family engineers used to protect data against corruption in transmission, cousins of the codes that hold a video stream together across a noisy connection. Gates described the finding in Physics World in 2010 under the title Symbols of Power, and has returned to it in lectures ever since. Here is where the accuracy matters, because this entry is almost always reported wrong. Gates found these codes in the equations of supersymmetry, not in the cosmic microwave background. The widely repeated claim that error-correcting codes were detected in the CMB does not trace back to a paper, it traces back to a game of telephone. The CMB does contain genuine, unexplained anomalies: the cold spot, the hemispherical power asymmetry, the alignment of the low multiples that Kate Land and Ju Mugwejo named the axis of evil in 2005, all confirmed by Planck in 2018, but those are anomalies in a temperature map, not codes. And Gates's own codes may simply reflect the combinatorial structure of the representation theory rather than anything about reality. He has said as much himself. The honest position is that a real, strange, unexplained mathematical coincidence exists, and the internet attached it to the wrong dataset. There is a lesson in the mangling worth more than the mangled claim. The story spread because code found in the sky is a better sentence than codes found in supersymmetric representation theory. One is an image, the other is a result. The version that traveled is the version that lost its citation. Sitting comfortably with the second sentence is roughly the whole difference between an argument and a mood. Why would error correction, a concept invented to fix a specifically engineering problem, show up uninvited in the algebra of matter? None of it settles what happens when someone actually looks. Number 2. The looking problem. Thomas Young was settling an argument about optics in 1801. Newton had said light was corpuscular, others said it was a wave. Young cut 2 slits in a card, shone sunlight through them, and looked at the pattern on the far wall. It was a decisive, boring little experiment with a clear answer: interference fringes, therefore waves. He was not opening a 2-century wound in physics. He was closing a debate. Send particles through 2 slits one at a time, and the classical expectation is obvious. Each particle goes through one slit or the other. Fire enough of them, and you build up 2 bands behind the 2 openings. That is what marbles do, what bullets do, what anything with a definite trajectory does. Electrons build an interference pattern instead. Then you place a detector at the slits. The pattern collapses into 2 bands. The effect scales absurdly far up. Clinton Davison and Lester Germer had already caught electrons diffracting off a nickel crystal at Bell Labs in 1927, more or less by accident, after a bottle of liquid air broke and forced them to re-anneal their sample. Akira Tonomura's team at Hitachi filmed the buildup directly in 1989, firing electrons one at a time and watching individual dots accumulate into fringes that no single electron could have known about. Marcus Arndt and Anton Zielinger's Vienna group ran it with 60 atom-carbon 60 buckyballs in 1999 and got interference from an object with a defined temperature. Later work pushed the record past 2,000 atoms. Wheeler's delayed choice version, deciding how to measure after the particle has already passed the slits, was realized experimentally by Vincent Jacques and colleagues at the Institut d'Optique and published in Science in 2007. The result held. The quantum eraser experiment of Yoon-Ho Kim, Marlon Scully, and colleagues, published in Physical Review Letters in 2000, restored the pattern by destroying which path information after detection. The interpretations are a graveyard. Copenhagen says the wave function collapses on measurement and refuses to define measurement. Many worlds keeps the mathematics clean at the cost of an unobservable branching multiverse. Pilot wave theory restores determinism, but requires explicit non-locality. Decoherence, from Dieter Zeh in 1970 and Wojciech Zurek after him, explains beautifully why we never see macroscopic superpositions, and does not explain why we see one specific outcome. 125 years on, the community has no consensus. A 2011 poll of physicists at a Foundations conference in Vienna returned a split across at least 5 interpretations with no majority. The computational reading is the one that keeps people awake. A rendering engine does not compute detail nobody is looking at. Something in nature declines to commit to a definite state until the information is extracted. And that is exactly the optimization an engineer would build. If reality holds off on deciding until it is measured, what is it doing in the meantime? The last one is not an interpretation. It is mainstream physics, and it is worse. Number 1. The boundary. Jacob Bekenstein was a graduate student under Wheeler at Princeton in the early 1970s, worrying about a housekeeping problem. Throw a hot cup of coffee into a black hole and its entropy vanishes from the universe, which violates the second law of thermodynamics. Wheeler mentioned it almost as a joke. Bekenstein took it seriously and tried to save the bookkeeping. Entropy in every ordinary system scales with volume. Double the space inside a box, and you double the number of possible microstates it can hold. That relationship is so basic to statistical mechanics that nobody states it. It is the assumption underneath the assumptions, and it holds for gases, solids, and every laboratory system ever measured. Bekenstein's answer scaled with area, not volume. The surface. Bekenstein published the proposal in 1973. Hawking, who initially thought it was wrong, made it exact in 1975. A black hole's entropy equals precisely 1/4 of its event horizon area measured in Planck units. Every bit of information about everything that ever fell in is accounted for by the boundary, and nothing is accounted for by the interior. Gerard 't Hooft generalized this into the holographic principle in 1993, and Leonard Susskind published The World as a Hologram in the Journal of Mathematical Physics in 1995. Juan Maldacena's 1997 correspondence between anti-de Sitter space and conformal field theory turned the idea into working mathematics, a gravitational theory in a volume shown to be exactly equivalent to a theory without gravity living on its surface, and became the most cited paper in the history of theoretical high-energy physics. The attempts to make this ordinary have all stalled. It might apply only to black holes, but the Bekenstein bound applies to any region, capping the information any volume of space can contain. It might be a mathematical curiosity of anti-de Sitter space, which has negative curvature and is not the geometry of our universe accurate, and 3 decades of effort have not produced a de Sitter version that works. Craig Hogan built the holometer at Fermilab, a pair of 40-meter interferometers specifically to detect holographic noise, and reported in 2015 that the effect was absent at the modeled scale, which killed one particular formulation and left the principle entirely intact. Maldacena and Suskind's 2013 ER equals EPR proposal deepened the puzzle by tying entanglement to wormhole geometry rather than resolving anything. Nobody has explained why the information content of a region is fixed by its surface rather than its bulk. It is simply what the equations keep saying. Read that plainly. The 3-dimensional world you are sitting in. Your body. The room. The distance between you and the wall carries no more information than could be written on the 2-dimensional surface enclosing it. Depth may be reconstructed, not fundamental. Every physicist above takes this seriously, and none of them started out looking for a simulation. If everything about a volume can be encoded on its boundary, which one of them is the original? 10 entries, and not one of them lives at the edge of what we know. Landauer's principle is measured in a laboratory. The GK cutoff is confirmed. Holography is where the field's best minds have camped for 30 years. Every anomaly here sits in the load bearing walls of our most tested theories, not up in the attic with the speculation. The universe is not confused about what it is doing. We are the ones squinting at a readout that came back 120 orders of magnitude off and deciding to file it as a rounding error. If you want to see more videos like this, click the video on screen now.